All right, so let's move into sort of the coding of machine learning. One thing about this is you can use this free Google environment, which I highly recommend, colab.google.com. This is free Linux environment. You don't have to install anything. It gives you Python coding, and it even gives you a GPU to some extent if you need it. So you can do a lot here, and it doesn't matter what kind of machine you have. You don't have to install anything. You could, of course, use a virtual machine or something, but this is a nice environment to work in. And we're going to use the TensorFlow library for this one. There are several libraries for machine learning, which is why everything is easy in Python, because people have written libraries to do all the hard work. You just had to figure out how to use the libraries, and they're not too complicated. So we'll start with this one here. What we're going to do, not that one, this one. We're going to do the simplest machine learning. I mean, the point is, normally, if you have the intelligence would all have to be added by a human, and the machine wouldn't learn anything. And this is the simplest machine learning. What we're going to do is simple curve fitting. So suppose you have some data like this. X goes up by 1, and Y is here. If you look at this, you can pretty quickly see with X goes up by 1, Y goes up by 2. So the equation is Y is 2X minus 1. A human can find that. And we want to write machine learning that will figure this out, which would normally take a human to do, to find the pattern. So this is the code that does it. You import TensorFlow, and then here's the data, just the X's and the Y's, and then you just fit it, and this fits it with a process called stochastic gradient descent, which is a general solution. And what this does is it makes one neuron. And the neuron just does a linear combination of the input. In comes one input, it just multiplies it by a parameter m and adds another parameter. That's it. And all it's going to do is try to find the values of those two parameters. And the way it does it is by having a loss function, which it calculates the values of all these points and decides how far it is from hitting them. And then stochastic gradient descent starts the parameters at a random value, and then it just changes the parameters by a small amount. And it can figure out, by doing partial derivatives, it can figure out what direction would decrease the loss by assuming it's locally linear. And if you take a small step, you assume the curve is not too large in the size of that step. So by taking 500 little steps, it will change the parameters to make the loss smaller and zero in on the right answer. So let's run this. There in the first one just to see that I have TensorFlow installed, which I do. Here's the next one that will do the 500 steps. So if I run that one, you see here it goes. It's only taking, a small amount of time to do each step, and the loss is going down. If you go up here, loss was 5, then 3, then 3, then 2, each, because it can calculate what direction should lower the loss, and it just takes a step. After a while, the loss is going to get very small, 0.004. We get down to 500 steps. The loss is getting down to 10 to the minus 5, very minor, because the data was perfect. There was no error in the data. So you can perfectly fit it. So he's able to get the loss down very far, and to test it, I had it predict the value at x equals 10. The right answer is 19, 2x minus 1, and as you can see, it got 18.98, so it's very good at predicting it. And this is fine. And the other thing, you might want to see what parameters it found. So I made one here where we'll just print the weights at the end. The weights are the parameters. And this model only has 2 weights, of course, so again, it's going to do 500 steps of gradient descent. And when it's done, all right, there we are, there. And this is a very simple problem, so it doesn't take much calculation. It only has to calculate like 10 points worth of error. See, there's the error getting very small again, 10 to the minus 5. And there's the answer. So it was 2x minus 1, and it found 1.99 for 2 and minus 0.99 for 1. So it got within 1% of the right answer, and that's the simplest case of machine learning. It is figuring out a pattern that it would normally have taken a human to figure out, that there's a pattern there. So now you can play some games with it to see it go. You can try adding errors to the data. If you do that, the error, I just put random errors on the y values. And then, of course, the error will not get as small, but it will learn approximately the right curve. And then you can try fitting something that is not a straight line. This is a parabola, and therefore it will try to fit a straight line through it anyway, but it will have a high loss even at the end. It can't do a good job fitting it. And so then you can fit a more complex curve. So here, instead of having just one neuron, we're going to have one input neuron, and then that's going to feed into a hidden layer of neurons that take the input here and process it. And each one in this layer is going to feed into the neurons in this layer, so you have many more parameters. This is a linear calculation. This is another linear calculation, combining those, and then one output layer. So you have a hidden processing here. This is the way the brain works. And in that case, now you're going to have a lot more parameters. So if you run this one, you can now fit complicated curves like this. And this curve is x times cosine x plus some random noise. So it's wavy and varied. But of course, you have hundreds of parameters now. And you can see how it goes. And now here's the number of parameters. The total number of parameters is 228. Really a lot of parameters in this one, like 4,000 or so. And now you can play games with it. Now this is how you make a multi-layer model. All you do is add a couple lines. This is the input layer with 1 unit. Here's the hidden layer with 64 units, and another hidden layer with 64 units, and the output with 1 unit. That's all you have to do is add these lines. So you can now modify it. You can remove some of these lines to make the model simpler. So you can try remove one of the layers, so you only have one hidden layer. And in that case, it's still pretty good, although inferior at fitting. And now you can try various combinations. So 32 units per layer, 1 layer, 16 per unit, 2 layers, 4 units per layer, 3 or 4 hidden layers. You can try various combinations and see how good they are. And there's flags to find here. So you can get a clue how to work this. You can change to have a different number of points, a different amount of noise, and see what that does. So it's sort of interesting to get to see a little bit of simple curve fitting here. And for even more fun, you can go to this one and start doing computer vision, which is where you begin to see how powerful it is. And I was amazed how powerful it is, even using these free Google Colab machines, which are like our Kali virtual machine. It doesn't have much resources. It's not a very powerful machine, but it doesn't have to be. And so what we're going to do is take this fashion database, this is a famous database for machine learning, of clothing items. And they a whole bunch of pictures, and they fit into 10 categories: t-shirt, trouser, dress, sandals, shirt, and so on. And the task is to separate them into these categories. Look at the picture and decide which type of clothing it is. So what you do is you take the input image, and here's where I began to get really upset, because I used to do brain models of computer vision as a scientific research. I used to be in medical research. And you take the pixels and treat them all as independent data and just feed them into a neural net, which, by the way, is incredibly stupid and wrong. This is not what your brain does. Your brain detects features like this is background, this is foreground. Then it detects features like this is a line. So the fact that these dark pixels are all in a row matters. And here you discarded that. You treated each pixel as just an independent piece of data. You've included nothing about the relative position of the pixels, which is important. However, you can use this and you will get some ability to learn. It's just going to be very inferior to something that used a smarter way of processing the data first. Anyway, so you take the pixels in, 784 pixels per image, and we just feed them into a hidden layer of neurons, and then we have 10 output layers. And the output, the signal on the output is going to be the probability that it's a coat or a sneaker or a bag or so on. So here's the code. We can just feed that into this model here. I could make a fresh new model, but I think I'll do that. Let me make a new one there, just so it's clean. All right, so I feed in that code, and it's going to load the data from a database that it has access to, and it's going to run it and fit the model. And by the way, when you do this, you take the input data and you take a portion of it to train on and a portion to test on. Typically, you take 80% of the data and train on that, and 20% you use to test it. So you show the trained model images it has never seen before and see how accurate it is. This is an important way to do it. And so here it goes. It's downloaded the data. Now it's going to do 5 epochs of training. And see, the loss is a measure of how wrong it was, because the data is labeled. So you know the correct category for every image, so you can measure how many of them correct. So it's 0.6, going down to 0.3, down to 0.34. So you see it's working. The loss is going down, and the accuracy is going up. This is the percentage of the, I think this is the percentage of the training data that it got right, 78%, 80%, 87%. You see it's going up, and there you are. So, all right, let me go to my instructions, find out if I can remember. I don't remember what some of those numbers mean. Yeah, so, all right. The second number is actually the model when applied to the test set. So it is, yes, 89% accurate on the training data and 87% accurate on the test set, which is what you would expect. The test is not quite as good. So that's a pretty good model. And let me just clean off things that I don't need here. All right. And so now we can view the results for 20 test images. So this will print them out so we can see what they look like. All right, and what this is the model. The first image is really a number in category 9, and here's the output, and the output is 98% of category 9 and a couple other percentages here. So it got the first one right. The second one should be a 2, and you can see 2 is 99%. This one should be a 1, and that's 99%. So these ones it's doing very well. Now it's going to get some of them wrong, like here, 82%, being a 4, but it had a 15% chance of being a 2, but it still got it right. This one here it might have got wrong. This is really a 7. 0, 1, 2, 3, 4, 5, 6, 7. Nope, it got it right. The biggest number is 7. Usually you can find ones that got wrong. Here it is. This is a 4, but it thought it was a 2. 4, it only had a 5% chance, but it decided it had a 92% chance of being 2. So this model it got wrong. Now these were from 0 to 19. So 19, 18, number 17 it got wrong, and number 1 it got right. So let's take a look at one it got wrong and one it got right. It's different every time because there's some randomness in the process. So mine it was 1 and 17 I want to compare. So this is 0 is fine, 17 is the one I think it got wrong. There we go. Let's see what they look like. So there's one it got right, and this is one it got wrong. It couldn't tell if this was a category 2 or a category 4. And if we look at the categories, 2 is pullover and 4 is coat. And I don't really know the difference between those either. So, with this thing, it couldn't say if that was a pullover or a coat, and I can understand that. That's a difficult distinction to make. So it's kind of reminiscent of humans, even though it is not doing what humans do at all. Like as a human, when I look at this, I see the stripes. But it treated each pixel as just a completely independent bit of data. It did not notice or care that these are in any kind of pattern, which is amazing it can get anything done at all. And so, anyway, you can train the neural network. You saw the accuracy with all that go by. Okay. And now you can train it more. If you train it for more epochs, 25 instead of 5, then you'll have what's called overtraining. It's going to get better in that there should be 2 numbers at the end, which I'm having trouble finding. Yeah, here it is. So now it got up to 94% on the training data, but it's only 88% on the test data. This is overtraining, and this is a common problem. When you overtrain, it memorizes the test data, and it doesn't get any better at the training data because it's fitting not only the trend, but the noise. It's spiking every point. This is what's wrong with large language models, and this is a huge problem that may be the end of the whole industry because they trained the large language models, they trained them on all this data they found on the internet. And they apparently also went to pirate sites and took a lot of copyrighted books and trained on them, and the authors suspected this, so to prove it, the author would take like the first paragraph of Harry Potter and put it in GPT-4, and it would just print out whole pages of Harry Potter because they overtrained it and it memorized the test data. And the same thing in New York Times articles, and the New York Times sued, and the New York Times said, you copied our content and you're distributing it without permission. And the LLM people said, no, we just read your content the way a human would to understand the general gist. We didn't just copy every bit of it. And they said, well, this is the test. If it spits out exactly verbatim what came in, then it did just memorize it. And of course, the legal argument will depend on different subtleties, but that's the issue. That's what overtraining does. It memorizes the training data, which is not really learning the trend, which applies also to the test data. It's a big issue. Anyway, so it's interesting to play with and get you started. And I think that's all I wanted to show you today. That's enough. But it'd be good to play with these. And it's, like I say, it's amazing how powerful it can be with such a stupid model that doesn't even do obvious things like find the shapes and patterns, and that doesn't require hardly any processing at all. So that's it. I'm going to stop this one.